So I'm going to use the Babylonian method to calculate the square root of a number. And I'm not going to show you the pseudocode. I'm going to just do it and talk my way through it. And I will show pseudocode. But I'm going to keep it abstract. So our pseudocode is like this. We read in a square. We're going to read in a value and we're going to call it square. And then, let's see. We're going to calculate the square root. I'm following your book, so I apologize. I said I wasn't going to write pseudocode, but I'm going to do a lot of it. We're going to calculate the square root, but we're going to follow this development of the algorithm from abstract to more concrete steps. And then we're going to write out the square and the square root. Okay, so there's 3 steps, but I'm sorry, 1, 2, 3 steps, but step 2 is magic. So we need to drill down a little bit on that guy. So in order to calculate the square root, how do we do that? So number 1 is we're going to use a method where you have an error. So basically you make a guess, and you keep improving the guess again and again and again. So I guess number 1 is going to be make a guess. To a new guess, right? I'm putting it in red because how do you guess the answer? So this whole strategy for doing the square root goes like this. You make a guess, and then you set the error to 1. Actually, you set the error to something really big, right? So you just assume that your guess is way off, right? And that makes sure that you can enter, this should have been black. You set the error to something really big. And now we're going to kind of go into this loop. As long as the error is greater than the maximum allowed error. So that's our tolerance. So we want to be within 0.001 of the correct answer. So we set our error to something incredibly big, and then as long as the error is bigger than 0.001, what we do is we get a new guess. So we calculate a new guess. And once we calculate the new guess, we update our error. So we don't know how to do this yet, so I put it in red. And we don't know how to come up with an initial guess, so I put it in red. But we do know how to determine the error. Our error is going to be, there's a couple of ways that we could determine the error, but if we've got the square root calculated correctly, then the error, so then our guess, if our guess is correct, then the guess should be the same as our square divided by our guess. If those two numbers are the same, then guess is the square root. If they're different, then however much their difference, that's a good estimate for how far off our guess is, right? So this is a little bit different than the way your book determined the error, but I'm going to set the error equal to the magnitude. So if I take guess minus square over guess, that should be equal to 0, right? If it's less than 0, then one of those numbers is wrong, and if it's bigger than 0, then one of those numbers is wrong. But I don't care which direction it is. So my error is going to be equal to the absolute value of the difference between my guess and the square root divided by my guess. So my error equals, or it gets, however you want to write that, the absolute value. So you can't type in those vertical symbols have a different meaning in both programs. So there's a function called absolute value of my guess minus the square, the original input number, divided by my guess. So that would be my error. And I'll keep updating as long as that error is bigger than the tolerance. Right? So I know that the number of digits here is how accurate my square root is. And the reason that I prefer this for estimating the error is because these are the number of digits of precision in my answer. The ones from the book, this number of digits is the number of precision like squared or something. So here's some pseudocode for how to calculate a square root. And it's missing some parts, so we need to drill down further. So we need to figure out how we calculate a new guess and how we choose an initial guess. And but we've seen how to get the error. The error is the difference between our guess and the square number divided by our guess, which tells us a little bit about how we might want to calculate an improved guess. So how can we calculate an improved guess? We want the difference. We want our guess to be somewhere in between the old guess and the square divided by guess. All right? We want the difference to be smaller. So the basic idea is to go halfway in between. So halfway in between guess and square of guess over 2 would be to set the new guess. Set that new guess to be the old guess, and halfway between guess plus square over guess, you get halfway in between by adding them and dividing by 2. So generally halfway in between a and b is going to be a plus b over 2, right? That'll get you halfway in between those two numbers. You can kind of work that out. So this guess is halfway in between my guess, which is maybe an overestimate, and square over guess, which would be an underestimate, or vice versa, right? So hopefully this guess is a little bit closer to the truth. So now we kind of see how we've drilled down and we know exactly how to do this. So this is completely specified. We just don't know how to come up with an initial guess. And the cool thing about this method is it doesn't really matter how we do it. So one way that your book comes up with, which is pretty arbitrary, is set guess equal to square divided by 4. Okay. So now we've done it. We've got no more pieces that remain red. So we can actually write the whole algorithm out right now. It goes like this. We say read square. And then instead of, say, calculate the square root, we're going to come over here, and we're going to come over here and say that we're going to set guess to square over 4. And we're going to set the error to infinity. And while, by the way, you don't have an infinity number on your keyboard, so you can just pick any number that's bigger than your tolerance. It doesn't matter. Often you'll see people just write infinity for that, and I like that. So while the error is greater than our tolerance, we are going to calculate a new guess. So in order to calculate a new guess, we set guess to guess plus square divided by guess divided by 2. And then we have to set the error, right? So we set error as the absolute value of guess minus square divided by guess. Right? And then we repeat. And when we're done, so this will have finished, we can print out the answer. So we can print or write square, and then we can write what our guess is. So if we try to trace this with a number like 64, so let's imagine that we're going to trace the execution of this program. We read in square, and we get a 64. And I just want to point out one important thing about this type of algorithm is that because it's based off of taking a guess and then making a guess that we know has error in it and reducing the error in each step, if at any point you don't calculate the answer correctly, but instead you only approximately calculate, it doesn't hurt the method. So this is forgiving. And that's important because computers often have rounding error. And people often just have human error, which I will probably have. But rounding error is a real issue with computers. So, for instance, on computers, 0.2 plus 0.1 does not equal 0.3, it equals 0.300001, or something like that. And another thing about computers that relates to rounding error, if I wanted to do like the square root of 2, this algorithm has no hope. It would take an infinite number of steps. And that's why we don't actually go until the error is 0. We go until the error falls below some tolerance, right? So because you can't exactly calculate all square roots on a computer. It takes infinite digits, and we don't have those. So coming back here, we're looking at taking the square root of 64, and I'm worried that this might take math, but I'm only going to basically calculate one digit in every internal step. So if I have to calculate square divided by guess, I'm only going to calculate one digit of it, or one decimal place. And I made a mistake, so I'm going to trace through the execution of this code one more time. And I think what I'll do actually is I'll trace through the execution of this code on a separate piece of paper. Right. So we have we read in square as we trace through this code, and I'm going to use the number 64 because it's a nice power of 2. These numbers should work out well. I set my guess to something random, which is 64 over 4, and that's 16. And then I set my error to infinity, but really anything that's bigger than tolerance. So a value like 1 would work. And then I check error is greater than 0.01. So I'm going to set guess to guess plus square over guess. So the mistake that I made is I didn't update this thing enough. So what I wanted to do is I wanted to keep square over guess over here so I could easily keep track of it. Okay? So here my guess is 16, square over guess is 4 at this point in time. So guess is going to be 16 plus 4 over 2, which is 20 over 2, and that's 10. But now square over guess has changed. So now square divided by guess is 6.4. Right? So 64 divided by 10 is 6.4. And so when I calculate the error is going to be guess minus 6.4, which is 3.6. Does that make sense? So I just need to make sure that I update square over guess whenever I change guess. And now I come back up here to the error. The error is not below the tolerance, so I need to update guess. So guess becomes guess plus square over guess divided by 2. So that's half of 16.4, and that is 8.2. Once I update guess, square over guess changes to be so I'm only going to use one digit because otherwise I don't know how far it'll go. So there's other digits, I'm sure, but I don't want to keep doing it. I know that it's a 7.8 and change, and the idea is that this is forgiving to rounding errors. This is a rounding error. And I'm just going to say square divided by guess is 7.8 at this point in time. So when I calculate my error is going to be the absolute value of the difference between guess and square minus guess, which is 0.4. And then I come back up here. That's bigger than the tolerance. So I'm going to set my guess to be my guess plus square over guess. 8.2 plus 7.8 is 16, divided by 2, which is 8. And my error is the absolute value of 8 minus square over guess. So 64 divided by 8 is 8. So 8 minus 8 is 0. 0 is not greater than my tolerance. So I'm going to come down here, and I'm going to write out square and guess. So it worked. Just took a little tiny bit of math, actually, which you could have done on a calculator, but if you imagine that you're doing everything on paper, I mean, it's completely possible limiting yourself to one digit, because this is an example of a nice numerical algorithm. This is how old mathematicians like Gauss and people before the ages of computer had to calculate things, is they had algorithms, even though they didn't have computers, and a human being would follow them just like this, and you try to have an algorithm which is forgiving for human error. Alright, so that wraps that up, and I'll have to decide whether to edit out my mistake. So here, even though I kind of made some mistakes and didn't follow the algorithm correctly, I luckily still got an answer which is correct. So it's all good.